purpose of 2D kinematics, like 1D kinematics, is to analyze the motion of an object when its acceleration is constant. We will now apply kinematics to two-dimensional scenarios like the path of a punted football. In this scenario, the acceleration of the football after it leaves the punter's foot is a constant 9.8 meters per second squared directed down toward the ground. So since the acceleration is constant, we can analyze it with the kinematic equations to determine something like the distance the ball goes after it hits the ground, or how long the ball stays in the air. To answer questions like this, we will still use the kinematic equations that we learned about earlier, but now we need to recognize that many of the variables involved are vectors. In fact, they are all vectors except for time, which is a scalar. So that means that when we solve the equations, we must use proper vector math. As an example, let's say in the punted football scenario, we are given the initial velocity, the time the ball is in the air, and the constant acceleration. These three variables. And then we're asked to find the final velocity of the ball right before it hits the ground. So following the kinematics process discussed previously, we would then use this kinematic equation because it involves the variables in the problem. As it is written, we can see that we need to add vectors and multiply by a scalar, which is the time. So now we need to apply our vector math skills. As we know, to add these vectors, they must be in Cartesian form. So I'll expand the vectors like this. And then I'll multiply the scalar time against the two acceleration components, and we wind up with this equation. As we know, when adding vectors, the x components are added separately, and the y components are added separately. So we can rewrite this vector equation as two separate equations, one for the x variables and one for the y variables. So now, based on this result, let's step back and make a couple of very important observations. First, any vector equation in two dimensions can be rewritten as two separate equations, one for the x components and one for the y components, or three equations if we have 3 dimensions. And then second, the motion of an object in each coordinate direction is independent of the other directions. The first statement was basically just demonstrated when we had a kinematic equation that involved vectors and we rewrote it as two equations. We'll put this technique into practice in a minute and come up with an expanded procedure to solve kinematics problems. What I'd like to focus on first is the second statement. It stems from the two x and y equations that we wrote down a moment ago. Notice that the x equation does not include any y components, and the y equation does not include any x components. So the implication of this mathematical result is statement 2, that the motion of an object in each coordinate direction is independent of the other coordinate directions. This result is actually quite profound. To help you appreciate what it means, let me give you a couple of examples. Say an eagle has just caught a fish and is flying horizontally with the fish at speed v1. The fish suddenly wiggles free and falls back to the water following a path like this. As we know instinctively, the arc of the path depends on the speed the eagle is flying, which is the initial speed of the fish. If the eagle is flying faster at, say, v2, then the fish might follow along this path. Or if the eagle is flying even faster at speed v3, then the fish might follow along this path. And for the purpose of our discussion, I'll define the x and y axes in the usual way. Let's compare the three scenarios, focusing first on the x direction. As we said before, we're neglecting the effect of air resistance. So the only difference in each case is the initial velocity of the fish in the x direction. And as we can see, this affects how far the fish goes in the x direction. So now let's think about the y direction. The y component of the initial velocity is actually 0 in all three scenarios. So all of the variables in the y direction are actually the same. This means, for example, that the time it takes for the fish to reach the water, which can be calculated with a kinematic equation in the y direction, is the same in all three scenarios. I don't think this is an intuitive result for most people, but it is something that is borne out by the kinematic equations and by experimentation. It's also something that you may see demonstrated in the classroom. Here's another example to demonstrate this important independence of x and y motion. A train is traveling in a straight line on level ground and at a constant speed. The train has a flatbed car with a cannon mounted on it. As the train is moving, someone points the cannon straight up into the air and fires it. If air resistance is neglected, where does the cannonball land when it comes back down? Again, we want to analyze the x and y motions separately. In the y direction, the train and the cannonball have very different motions. The train doesn't move up or down, and the cannonball goes up and then comes back down again. But in the x direction, the train and the cannonball have exactly the same motions. They are both moving to the right at the same speed, and since we've neglected air resistance, they both continue to move at this speed indefinitely. That means that even though the cannonball goes up and back down again, it always remains directly above the cannon. That means when the cannonball comes back down, it goes back into the cannon. Again, this is not necessarily intuitive, but it's the way nature behaves. You can imagine a similar situation that's more intuitive for us. Consider a car that's moving in a straight line at a constant speed of 60 miles per hour. If a person in the car tosses an object straight up into the air, it will go up and then straight back down to the person's hand. It doesn't shoot back to the rear of the car. Something else I want to point out here is that the coordinate scheme does not have to be arranged so that x is horizontal and y is vertical. If the train is on a hill, say like this, we might decide to rotate the coordinate scheme as well for convenience, like this. But it doesn't matter. No matter how the coordinate scheme is oriented, the motion of the object in the x direction is still independent of the motion in the y direction. The only requirement is that the x and y axes and the z-axis, if we're dealing with 3 dimensions, must be perpendicular to each other. Now let's go back and apply the first rule to a kinematics problem. As a reminder, the first rule said this: any vector equation in 2 dimensions can be rewritten as 2 separate equations, one for the x components and one for the y components, or 3 equations if we had 3 dimensions. Since the 5 kinematic equations are vector equations, then each equation is actually 2 equations in one, or again 3 if we're working in 3 dimensions. So we can list the kinematic equations in 2 dimensions this way, where I've added x subscripts to one set of equations and y subscripts to the other set of equations. And now we can modify the procedure for 1D kinematic problems to include 2-dimensional applications. First, draw a simple diagram that includes the coordinate scheme, the directions, if you know them, of delta x, delta y, the initial velocity, the final velocity, and the acceleration, and show the initial and final positions of the object. Then second, make a list of the 5 variables in the x direction and the 5 variables in the y direction, and write down any of the known values. And then third, choose the appropriate kinematic equation to use in each direction and solve them. And then four, just double check to make sure that your answer is reasonable. Okay, so now I'll work through an example to demonstrate this procedure. A football is punted with an initial velocity of 22 meters per second, that is 50 degrees above the horizontal. If air resistance is neglected, how far will the football travel horizontally by the time it reaches its maximum height? Step 1 is to draw a picture with the key information on it. So here's the football with its initial velocity, and it follows a path like this, so it reaches the maximum height here. So there are the initial and final positions. Notice how I drew the final velocity, that it would be horizontal at this point. And now we want to determine how far the football has traveled horizontally. We can add to the picture that the acceleration of the football is always pointing down at 9.8 meters per second squared. And finally, we must define the coordinate scheme. So now the next step in the procedure is to list the 5 variables in the x direction and the y direction, and then add the data. I'll have to clear the screen to do this. Here are the 5 variables in the x and y directions. Let's just go down the list and see what we can fill in for each variable, starting with delta x. This is the variable we're trying to find, so let's put a question mark here. We're given the initial velocity, so we can find the x component of it with trig. Here's the initial velocity vector. We'll make a right triangle out of it. So now we can find the x and y components with these trig equations. The x component of the initial velocity comes out to be 14.1 meters per second, so we can add it to the list. Notice the x component is positive because we can see in the diagram that it points in the positive x direction. Okay, continuing down the list, we don't know the x component of the final velocity, and the acceleration is 0 in the x direction. This is an easy one for students to miss. It's 0 because there are no forces in the x direction. The only force acting on the football is the gravitational force, and it only points in the negative y direction. And now the last item in the list is time. We don't know what it is, so I'll put down a question mark. Now let's fill in the information for the y direction. Starting at the top of the list, we don't know what delta y is. We just calculated the y component of the initial velocity to be 16.9 meters per second, so we can fill in that value. Again, we know it's positive by looking at the direction of the vector in the diagram. Now let's consider the y component of the final velocity. This is another value that's easy for students to miss. The answer is that it's 0. It's 0 because the velocity of the ball at its highest point is horizontal, which means the vertical component of its velocity at this point must be 0. Next in the list, the acceleration in the y direction is 9.8 meters per second squared because the only force acting on the football is the gravitational force, and it's negative because it points in the negative y direction. And then the final variable, the time, is unknown. So now let's determine which kinematic equations to use and then solve them. In the x direction, we want to solve for delta x, but we only know two values in the list, the initial velocity and the acceleration. That isn't enough for us to solve any of the kinematic equations for delta x. A common technique in 2D kinematic problems is to solve for time in one direction and then use that time in the other direction. Time is the one variable that's shared between the two lists. So let's do that. Let's solve for time in the y direction and then use that time in the x direction. In the y direction, we don't know what delta y is, and we don't need to find it, so let's cross it off the list. And that means the kinematic equation to use is the one that does not involve delta y, which is this one. We had determined that the final velocity in the y direction is 0, so let's set it to 0 in the equation, and then solve the equation for time. Plugging values into the equation, we can determine what the value of the time is for the football to get to its maximum height, which is 1.7 seconds. So check to make sure that that seems like a reasonable amount of time. I think 1.7 seconds seems about right. So now let's include that value of 1.7 seconds for the time in the x direction. And now looking at the variables in the x direction again, we can see that the final velocity in the x direction isn't known and doesn't need to be determined, so we can mark it out, which means that this is the kinematic equation to use. Let's first simplify the equation by recognizing that the acceleration is 0, so the equation simplifies to this, and then plugging in values we can get our final answer, which is 24 meters. So check to make sure it seems like a reasonable value, and I think 24 meters for punting a football to its maximum height is a reasonable number. Okay, the last thing I would like to mention in this video is the term projectile motion. Recall when we discussed 1D kinematics that free fall refers to the scenario when the only force acting on an object is the gravitational force, which means that the acceleration of the object near the surface of the Earth is 9.8 meters per second squared toward the ground. Projectile motion is just basically the 2D version of free fall. So it basically refers to this scenario when an object is traveling through the air, but air resistance is ignored, and it is assumed that the only force acting on the object is the gravitational force. The football example we just worked through is therefore a projectile motion problem. One interesting consequence of projectile motion is that the path of an object in projectile motion is a parabola. Basically, it's the mathematical consequence of having a constant acceleration and solving the kinematic equations. Here are several images of objects going through the air, but the air resistance on them is small enough that we can consider them to be in projectile motion, and so they follow a nearly parabolic path. Here's a tennis ball, here's a ski jumper, and here's a water fountain. And so we can see the path for each of these objects is parabolic. Well, that brings us to the end of this video. Be sure to check out the worked out example on 2D kinematics that's posted on Moodle as well. Thank you.